Okay, let's get this show on the road.
Professor, can I
Hello,
ask a
everyone.
quick question?
Hope you're well. Welcome to another edition of Math 1207. Did someone say they had a question?
Yeah, I have a question. I was looking at like the review sheet, like the test one that on the, your website, the test one review.
Yeah.
I saw on that review sheet we have to know errors for like the error for approximating integrals, but in the notes it says we don't need to know it.
You don't need to know that.
Okay, so just like ignore that part of the review
just
sheet.
Ignore that part. Yeah.
Okay, thank you.
So the test is going to cover up to everything that we do today, and it will not include error bounds for the numerical integration.
Professor, because on like one of the homework assignments is for that.
Yeah,
so, like,
it'll stay on the homework, but you don't need to know it for the test.
Okay.
So you can use the formulas that I gave you in the packet for the homework. But yeah, I'm not going to test you on it. Okay. Any other questions before we? So yeah, a few announcements first. So we do have a test this Friday. It is going to be the entire recitation session. It is going to be essentially like a quiz. The difference is going to be that you have to upload work, you have to show your work. So when you answer certain questions, you're going to have to scan or take a picture of your work and upload it. You can access Gradescope from your phone, and on the upload button, once you click on that, it'll give you the option to actually upload a picture directly from your phone, either take a new picture, upload from the gallery, or you can use a phone scanner, cam scanner, doesn't really matter as long as you can get an image of your work upright, like not upside down or sideways, but get an image of your work on Gradescope. So that is the main difference. I guess another small difference between the test and the quiz will be, I won't really ask you any more like definition problems or formula problems. Like I'm not going to ask you like last time, what is the integral of tangent? Tell me the answer. Like I expect you to know that by heart, and that's just going to be assumed that everyone knows it at that point. So no real definition-ish questions or anything like that. I will be testing you on concepts. You will have to work stuff out, and you will have to show your work. And it will be the entire period as opposed to just half the recitation period. So those are the major differences. Covers everything that we will have covered up to today, which means it's going to cover everything we learned about integration, including numerical integration, not including errors. And it will include sequences and a little bit of series, because we're going to do some series today. Also, someone reached out to me. They were worried about the timing of everything with uploads and all that stuff. And since the test is already being pushed, because I mean, class ends at 9:20 on Fridays, but I pushed the ending of the test to 9:30 to give you guys an extra minute, a few minutes. And I think to push it anymore would not be too courteous to the instructors in your classes after mine. So I figured if I'm going to add any bit of extra time to account for technological difficulties and uploads and all that sort of thing, I would want to add it to the front end. So if I were to start the test earlier, like by 15 minutes, like at 8:15 a.m., would everyone be okay with that?
Yes.
Because if a bunch of you can't make it at 8:15, then it wouldn't be great. You know what I mean? Because then you guys would be at a disadvantage. Some people will be at an advantage. But it seems like most people are okay with that.
Would the test window still be 60 minutes, and then we just have a longer time after to upload?
Yeah, essentially.
Okay, so then it would just essentially end at 9:15 instead of 9 or whenever that math is.
No, I'll still put the extra time in the thing, in the window. So the window will be open from 8:15 to 9:30.
Okay, and then is it an option to just upload one big like assignment, quote unquote, with the work, or is each question individually you want just like the work?
So you have to upload work for selected problems. So there will be a few problems where I said, for this problem, upload your work.
Okay.
And you have to do it for each of those.
How many questions is the exam?
Depends, somewhere between 12 and 20 problems.
Okay,
If it's
thank you.
12, they'll be more involved. If I go up to 20, then a lot of that extra will just be concept questions that I would expect you to be able to answer in a few seconds.
Will there be extra credit on the
Yeah,
test?
there will be a bonus. So the bonus will cover pretty much everything up to 11.6. So today we should get through most of 11.2. If we're lucky, we might break into 11.3. But if you continue with the trajectory, because 11.3 through 11.6, they're kind of all about the same thing. So if you continue to the end of that section, which if we break into 11.3, you'll kind of have an idea of what you can do moving forward. But I'll probably put the bonus on the rest of chapter 11 up to 11.6. Okay, so that's what we'll do. Test this Friday, starts at 8:15, and it'll be like the whole time. And you have to upload your work. So make sure you know how to do that with your phone, and you don't actually run into any issues. I did put up a practice quiz 8, where I did require that you upload some things. That's not graded. It was just to make you used to what it would feel like to upload something on Gradescope, so that on Friday, you know what to do and everything will be fine.
Quick question, does that mean we're joining the recitation Zoom at 8:15, or does the test open at 8:15 and we're supposed to join the Zoom at 8:30 like usual?
For now, I would assume at 8:30, because I didn't run this plan by Professor Golek yet, so I don't actually know if he can log in early, but I will be sure to update you guys and let you know.
Thank you.
Okay, so there we go, sharing the screen. Let me make sure that I can see the chat and everything here. Okay. Okay, so that being said, anything else comes up, of course, you guys can email me. And for now, let's actually move into the matters at hand. First, a quick review, because, sequences was done all the way last week, and we're actually going to need sequences moving forward. So let's just remind you of what they are. Quick concepts here. Sequence is just a list in a definite order. For us, it's just a list of numbers specifically in a definite order. So it's just a list of numbers, and there's a specific way that I can attain each number. It's like determined, it's by a formula or some sort of method. I know how to determine the order of the elements. We can name sequences by lowercase letters, usually with subscripts, where the lowercase letter with a subscript tells you the term that's in the nth position. So we can see the A1 term, the A2 term, the A3 term, the A4 term, etc. A sequence can be finite, meaning that the list eventually stops, or it can be infinite. The infinite ones are the ones that we will care about for the most part. And when it comes to the infinite ones, they have this property, or they may have this property that we call convergence. And we say an infinite sequence converges if, when we take the limit as n approaches infinity, it approaches a real number. So this is kind of saying that the outputs tend towards some real number as you go along. And we see that sequences, we can kind of plot them. They're like these isolated dots that on all the integer values, there will be some real number output, and you can actually plot them in the 2D plane if you wanted to. And if these dots have like this overall trend and they're going towards something and they're settling towards something, we say that the sequence converges to that thing. It doesn't make sense to take the limit at any intermediate point, because limits need to be able to get close, and these cannot get close at any intermediate point. We went through just determining whether sequences converge or diverge. And converge just means, like I said, the limit approaches a real number. And diverge means all other cases. So whether it goes to plus infinity or minus infinity, or it doesn't converge, it like oscillates between some values or something like that, we say it diverges. We introduced some important ideas. These are probably mentioned as well in Calc 1, but for now, I consider this an introduction to the factorial. We only define those on the non-negative integers. 0 factorial is 1, and for every positive integer, n factorial, it's just the product of all numbers from 1 up to that number. We also introduced the idea of -1 to the n, which just alternates -1 plus 1 -1 plus 1, and we're actually going to use that to alternate signs later on, so that's something you should know about. And these are properties of convergent sequences. It does not apply if your sequence is not convergent, but if your sequences are convergent, then all the nice limit rules that you knew about from Calc 1 that worked for limits in Calc 1, they work for sequences as well. So that's good to know. Another important thing for us to know is when a sequence is decreasing. Of course, there are cases where you need to know when it's increasing and bounded and things of that sort as well. But decreasing is particularly important to us because of what we're going to need, some tests that we're going to need to do later on. So decreasing just means the outputs get smaller and smaller over time. So basically, you can identify that the n plus first term is going to be smaller than the nth term, or just basically identify that if your an can be written as a formula and that formula is differentiable, then you just see if the derivative is strictly less than 0, and that would mean decreasing, right? Just like in the Calc 1 case. So that was sequences. Sequences are a list of numbers in a definite order. If the list goes on forever, we call it an infinite sequence. An infinite sequence converges if when you take the limit as n approaches infinity, it converges to a real number. Otherwise, it diverges. Sequences we can track their trajectory to see if they're increasing or decreasing or neither. And being able to examine a sequence is important in all these respects. They follow these properties. Basically, the nice properties that you remember from limits. Limits were very nice in Calc 1, and the sequences continue that tradition. At least the convergent ones do. We also, again, covered this important relationship from Calc 1, and hopefully we remember that. Yeah, so that was the recap. Now let's actually jump into the new material. Okay, so now the fun begins. Series is the main thing that I wanted to cover in this class. We did need to talk about sequences though, because sequences are important for understanding this topic. And a lot of things we define for this topic will be defined in terms of sequences. But series is the main goal here. I need to get you guys to know about the basics of dealing with series. Series, super important. They're a super important topic. It turns out a lot of the times, even when you're asking your calculator to do something or your computer to do some sort of calculation, a lot of the times, unbeknownst to you, your calculator or your computer will actually transform your problem into a series and actually use a series to answer the problem. And then it will convert the answer to something that you understand and put it up on screen. So we're going to see some of that kind of thing, some inner workings of series, like how we would compute certain things, how we would approximate certain things. Like if I told you that, the integral of something, some function doesn't have an antiderivative, and you plug into Wolfram Alpha or a calculator and says, okay, integrate from 0 to 1 of this function where it's impossible to integrate. Like, how does that thing figure out how to tell you a decimal approximation for the answer? Because it does, and it can, and these things happen, right? So when you see in statistics and you're looking at normal curves, and you want to find the area under the probability density function of a normal distribution, that is technically you have to do an impossible integral to actually do that. How do you go about computing things of that sort, right? So chances are your calculator or your computer is going to use series to calculate this, as well as some other things. So series is a very important topic. It does not only apply to calculus, it applies much more broadly. Although you can't really think of it as being separate from calculus because we can use calculus techniques with series. But at the end of the day, I just want to kind of bring it to your attention. Series are super, super important. You do want to know a lot about them. And whether you're going into pure math or applied sciences, knowing about series will make that endeavor a lot more understandable. Okay, so I'm going to start with a little bit of motivation, kind of a little story here. We're going to talk about Zeno's paradoxes. Right, so Zeno was a philosopher from like 450 BC, around that time. And he wrote a bunch of paradoxes because, you know, that was a nice little pastime at that time. Most of these guys were lost. I think, you know, when the Library of Alexandria was destroyed by flames, a lot of the paradoxes were burnt up, but some of them survived. Plato talked about them, Aristotle spoke about them. But one of the famous paradoxes is called the Dichotomy Paradox. So basically Zeno was reasoning like this. So Zeno basically thought, well, to get anything done, you have to first get a part of that thing done, right? Like if you say, I'm going to clean my room, there must come a point where half the room is cleaned, right? And you have to clean the other half, right? As you go through the process of getting something done, it's a process, right? Like, so things get done in parts, right? So he asked the question, okay, so let's say we're going to walk a mile. Before we can walk a mile, we actually have to cover half of a mile. And before we cover the remaining half of a mile, we have to cover half of that remaining half, which is another quarter of a mile. And before we can cover another quarter of that mile, we have to cover a half of that half a mile, which is an eighth of a mile. And then before we can cover that, we have to cover half of that distance. So basically, like kept saying, in order to cover some distance, you have to first cover half the distance, and then you have to cover half that distance. Then you have to cover half that distance. So his paradox was, how does anything actually get done? Essentially, what you can do here, as you're seeing, is you're kind of dissecting a mile into an infinite sum, essentially. So if you look at this equation right here, you'll see that basically how he's conceptualizing a mile, walking a mile, is you walk a half a mile, plus you have to walk a quarter of a mile, plus you have to walk an eighth of a mile, plus a 16th of a mile, plus a 32nd of a mile, plus a 64th of a mile, et cetera, going on forever. And so he's like, well, to be able to walk a mile, essentially you have to be able to add up an infinite number of distances. That's impossible. How does anything actually get done, right? And so this was back in the day, and we're talking about a millennia and a half ago, was a topic that was debated. Like, how does anything actually get done? Can you actually do this, right? So now this idea, the thing is, of course, it's very strange that this would be the case, that we wouldn't be able to add this up, because we actually walk a mile every day, right? People walk miles all the time. There must be a way to actually accomplish the feat, right? Even though technically, yes, you can think of it as being broken up into parts. So there was the intuition that an infinite sum of this sort should have some meaning. But we couldn't really assume it had some meaning, because yes, mathematics is often useful in real life, and it describes reality very well, but you can't always assume math is going to follow reality, because it doesn't always. So now we have to try to figure out, the math people have to figure out, what does it mean to add an infinite number of terms? Is it even possible? Will this ever make sense? And of course, the calculus students at this point is going to scoff at this, because you guys all know that you can do this. I mean, that's what integration is, isn't it? Right? When you had to do integrals in Calc 1, what was it? You set up a Riemann sum, and then you pretty much let the number of subintervals go off to infinity, essentially to compute the area by a definite integral. What you essentially did was you added up an infinite number of areas of rectangles, right? And this guy we call the integral. The integral was just a very sophisticated adding technique, a very sophisticated way to add areas of rectangles. And we sort of saw that this was connected to antiderivatives, and that's how we figured out a shortcut to actually do this. But now we're actually thinking more general now. Is there a more general idea for what it means to add up an infinite number of things? What if we don't know about antiderivatives? What if the context is not an integral at all? Does it actually make sense to actually add up a sum like this? I mean, if it doesn't always make sense, when does it make sense? Okay, so that is kind of the motivation that's going to start this whole topic, right? So at first we have to, of course, if we're going to actually use math to do this, we have to kind of set up a structure around it, set up some definition of terms and just how we want to think about this. And here's where sequences come in. So a sum of this sort, a general term for sum is the word series. So in math, when we talk about a sum, another word for sum is series. And especially when we talk about an infinite sum, we tend to call it an infinite series, or most people just say series. They leave off the infinite because 99.9999999% of the time, when someone says series, they're talking about an infinite series. No one's going to call a finite sum a series, right? Like if you're adding two numbers, I'm not going to say it's a series of two numbers. No one talks like that. But when you're adding up an infinite number of things, we call that a series. Series is just another way for name for sum. And it brings with it a bigger connotation, kind of like how derivative is another name for slope, right? But the derivative is meant to convey like, well, it's slope in a more general context than you're used to. In the same way, series has that connotation. It's summing, it's adding things up, but in a more general context than you're used to. In particular, in a context where we're adding up an infinite number of things and somehow trying to find meaning from that. So how do we start to get meaning? Well, we start to build up some structure around it, as I mentioned, and we come up with this definition. So a series is the sum of the terms of a sequence. So here's where sequences come in. This is how we're going to conceptualize. So if I have a bunch of numbers that I want to add up, the first thing we're going to do is put some order on those numbers, put a structure on them. So we're going to pretend that, you know what, these numbers belong to some sequence, right? There's a first guy, a second guy, a third guy, a fourth guy, etc. And we're adding up all these guys. So series we can define as the sum of the terms of a sequence. There is a list of things, and I want to just add up things in the list, okay? So whenever you have a sequence AN, right, where the terms are A1, A2, A3, etc., I can add all these guys up, A1 plus A2 plus A3 plus A4, add them all up, and that gives us what we call a sequence, a series. That's going to happen all the time today. That gives us what we call a series. It's the sum of the terms. Now, if that list happens to be infinite, you get an infinite series. And the notation is this, the sigma, right? You guys have seen that before. That was in Calc 1 when you were doing Riemann sums. So this says n goes from 1 to infinity, meaning that the n, it starts at A1, then A2, then A3, and you add them all together. So this is basically just another way of writing this. Going on forever. Of course, you can have a finite series as well. So we can go from 1 up to, say, k, where k is some finite positive integer. And that just adds up a list of k things. Right? But, I mean, adding up a list of finite things, come on, we know how to do that since grade school. I mean, it'll take a long time probably if there are a lot of things, but we understand that addition process very well. The process that we don't understand is being able to add an infinite number of things, right? So that's what we are really going to focus on. The infinite series is going to be our focus. So infinite series, this is the focus. We'll leave the finite series to the grade school kids. Okay, all right, cool. So hopefully everyone understands the idea of what a series is. It's just adding up a bunch of terms, basically. It's like a generalized version of addition. And in particular, we are concerned with being able to add up an infinite number of things. What does that mean? Can it mean something? When does it mean something? When does it not? Right? These are the questions that we want to ask. So many questions. First, we have to define some things, however, as well as notation. And I do want to mention the name of something. So there's something called the indices. This is plural for index. And the index of a series is just the guy that you use to number things, right? So the n here, or the n equals 1, this is called the index. It's called the index of a series. Okay, just in case you hear that phrase somewhere, or I mentioned the index of something. I'm talking about the numbers, the guy that's keeping count of the people you're adding up. That guy is called the index. So n here is keeping a count of the people who we want to add. In this case, it's saying we want to add all people from the first position going on forever. Okay. So now the question is, how do we make sense of something like this, like the infinite series? If there's an infinity on top, what does that actually mean? So what we want to do is, because we always want our mathematics to be consistent, whatever idea we apply to the infinite case, it should be able to generalize to the finite case. So whatever I say about adding up an infinite number of numbers, it should actually make sense with adding up a finite number of numbers. Because if I have to totally change what it means to add, then this would lose the sense of the meaning that we were after in the first place. So let's actually look at a finite series, just to kind of get an idea of how we'd want to define what it means for an infinite series to add up to something. And then we'll run with that. So suppose we wanted to add these numbers, 1 plus 2 plus 3 plus 4 plus 5. Okay. Now, yes, we could add them all at once, but how would you add this if you were in grade school? Let's say you gave someone who just recently learned to count, well, a little past recently, right? So they're not counting with pebbles anymore, but you gave someone a list of this. How do you think they would add it up? What do you guys think?
1 plus 2, and then add that to 3, and then to 4, and then to 5.
Right, exactly. Yeah, makes a lot of sense. You add 2 at a time, and then you keep adding 1 to the answer, then add 1 to the answer, then you add incrementally. So when you have a bunch of things in a list, a very natural thing to do, like you guys even just said it yourself, is to just add incrementally. You start by adding up the first few terms, and then you incrementally keep adding each new term and see what happens. So we can do that here, right? So you start to add all the terms. So we have the 1, then we add the 1 plus the 2, that gives us 3. Then essentially we're going to add the 1 plus the 2 plus the 3. In other words, we can add the 3 plus the 3 to get a 6. Then we're going to add a 6 plus a 4 to get a 10. Then we're going to add a 10 plus a 5 to get a 15. So essentially now, if we start to distill this thought process and we kind of try to track things very well. So we're like, okay, n is mentioning the number of the terms. And here we're looking at the number of terms we're adding so far, and here's the sum so far. And what I want you to appreciate is that these numbers will now have a definite pattern to them, right? The sum itself will create a list that's in a definite order. The list in this case is 1, then 3, then 6, then 10, then 15. And if anyone were to ask you, where are the numbers in this list coming from? You can describe to them a mathematical procedure for which to get the numbers in that list. So now it turns out that these sums that you're building up, what we will call partial sums, these guys can actually be thought of as a sequence. This is called the sequence of partial sums. So the term Sn is like the term that talks about the nth term in such a sequence. So it turns out when we can add these guys, we can add them, sequentially, one by one. And each time we track our current sum with a term in a sequence. This falls in line with the definition of a sequence. And now what you'll realize is that even in the finite case, what you'll realize is that once you actually move down this list, the farther you move down the list, the closer you actually get to the answer. You'll notice that the list converges to the answer.
Professor,
Yeah.
in the question, like in the example they were talking about the mile, technically, like if you're using that sum and like it was going to infinity, would technically the integral of that be 1 because that's the number, that's the mile you're walking, like you're walking 1 mile?
Well, the integral of what?
Of the sums, like the 1/2 plus the 1/4 plus the 1/8, all the way to infinity.
Well, no, to envision that as an integral would be a little bit more complicated because you have to figure out what your delta x is, what your f of xi is, and all that stuff. So it doesn't,
the limit
you
converge
can't,
to 1?
well, that's what we would expect, right? Well, we're going to see. Like, so
Okay,
at some point in this lecture, we're going to see. We're going to come back to that question. So that that was just kind of like my hook to kind of pique your interest into this question. We are going to go back to that whole dichotomy paradox and answer it. But right now, we're just building up the theory to be able to actually do that in some, not just because we feel like it should be add up to 1, because yeah, you're dissecting a mile by cutting it into halves. Makes sense that it should add up to 1. It's not good enough for something to intuitively make sense in mathematics. We have to have some kind of mathematical and logical structure behind it. So that's what we're building up, and we'll return to the problem later on. So here's the idea, right? I know that if I were to even add a finite list, this is a very logical way to add it. And I can describe this very mathematically, and I can talk about how the terms are adding up. So I can do that. And of course, the idea is the same. We are going to be able to define a term called a sequence called the sequence of partial sums. This is basically a sequence that's going to describe the sum so far, right? Where each term Sn describes the sum of the first n terms. And what we're going to do is we're going to just track the trajectory of that sequence. And essentially, for finite sums, we know that it converges to the answer. So we pretty much define that to be the answer in the infinite case as well. If we have an infinite sum, basically what happens is this sequence, the sequence of partial sums, becomes an infinite sequence. And then we pretty much try to see, does that sequence converge to something? Which now we know what it means for a sequence to converge. So if we have an infinite sum, what we can do is we can construct a sequence of partial sums and see if that guy converges, right? And that leads us to this definition, right? So this is what it means for us for a sequence, a series to add up to something meaningful. And we also use the language converges as well. So we also say a series converges to a number. And basically, intuitively, what we want to mean by this is that it adds up to this number. It adds up, and this is the answer, right? So we say a series, an infinite series in particular, converges to a real number S, and we can write this. The series n goes from 1 to infinity of an equals S if the sequence Sn converges to S. Otherwise, we say that the series diverges. Okay, so this is our now definition of addition. It works in the finite case, and we extrapolate it to work in the infinite case as well. It's a logically consistent way of adding things up. It makes sense not only in the real world, but in our math world. And the math world is actually the more important world right now in this context, right? So this is a mathematically sound way to define adding up an infinite number of terms. Pretty much describe the sum so far with a sequence and see what that sequence converges to. And if it converges to a meaningful answer, the series converges. It means that these infinite number of things actually add up to something meaningful in some sense. Otherwise, we say it diverges and the sum is just not meaningful. It's essentially you just wrote down gibberish, right? You essentially just wrote down infinity in a very complicated way, or something else in a very complicated way. So that's the idea. So let's actually go back to answer your question now to Zeno's paradox. With this construction that we just did, can we actually figure out how to add these things up? And so, yeah, let's actually try. So what we're going to do is let's create the sequence of partial sums. Okay, so what is S1? S1 is just the sum of the first term, so that's a half. So far, so good. All right, what is S2? Well, S2 is just the sum of the first two terms. So that's going to be a half plus a quarter. And that's going to be 3/4. Then we're going to find S3. That's a half plus a quarter plus an eighth. That's, of course, 3/4 plus an eighth. Can multiply the first fraction by 2/2 to add that. That will give me 7/8. S4, you see the idea, it's 1 plus a quarter plus a half plus a quarter plus an eighth plus a 16th. This is, of course, going to be 7/8 plus 1/16. Multiplying the first fraction by 2/2 and adding I would get what, 15 over 16, etc. Right now, of course, we don't want to do this forever. Like there would be no point if we're going to do this forever. So now the idea is I want to be able to describe this as a sequence and determine whether or not it converges. Now, of course, the nicest way to see this is to actually write down a formula for Sn and then take the limit as n approaches infinity. So based on what we wrote here, can you think of a formula that would describe, that would match these numbers? Does anyone see a pattern between the list? A half, 3/4, 7/8, 15 over 16? Any pattern?
It's like x over x plus 1.
X over x plus 1?
Yeah, for like some x. Obviously, you have to find the x, but like
One
is one less than
so you're
3 is
claiming
one
that
less than 4.
Sn is n over n plus 1?
No, just that the pattern between the sums. Never mind.
Oh, okay. All right. Yeah, but how do you find the x? What other pattern? So yeah, you notice that the denominator is always 1 larger than the numerator. Sure. Any other pattern?
It's 1 minus the last term in this series. So like the fourth one is like 1 minus 1/16. The third one will be 1 minus 1/8.
1 minus the last term?
Yeah, like if you look at the last one, 1 minus 1/16 is 15/16. 1 minus 1/8 is 7/8.
Okay. All right. How can you turn that into a pattern? So I see a comment in the chat here. 1 over 2 to the n. So they notice that the denominator is a 2 to the n. There's a pattern, right? Notice here, the denominator, this one is what? 2 to the 1, where the denominator here is 2 to the 2. Denominator here is 2 cubed. Denominator here is 2 to the 4th. That seems to be a pattern for the denominators. What about the numerators? Someone made a comment earlier that's going to tell us how to figure out the numerators, actually.
2 to the n and then minus 1.
To the n minus 1. So it's whatever was on the denominator and you subtract 1. Because the denominator is always 1 bigger. So we noticed that pattern before, and now we notice that the denominator actually follows the pattern of 2 to the n. So the numerator, it seems, follows a pattern of 1 less. And so this kind of tells us how to build up. Each term of this sequence can be described by this formula.
Couldn't you also simplify that as 1 minus 1 over 2 to the n?
You could. All right, so now by our definition, basically, so this means if I were to take 1/2 plus 1/4 plus 1/8 plus da da da, that is actually going to be equal to the series of, by the way, you can actually write that. Notice that each term here is also written as 2 to the n. This is like 1 over 2 to the n. This is like 1 over 2 to the 1. This is like 1 over 2 squared. This is like 1 over 2 cubed, etc. So each individual term actually looks like this. And I'm adding from n goes from 1 to infinity. That's essentially the series that we care about here. So the dichotomy paradox in terms of our notation can be written in this way. And according to our definition of what it means to add up to something, this is basically going to be equal to the limit as n approaches infinity of the sequence of partial sums. But what is that? Well, that's just the limit as n approaches infinity of 1 minus 1 over 2 to the n. And what is that?
Isn't that e?
No.
No, okay.
as the n increases, then our 1 over 2 to the n, that'll get closer. The 2 to the n, or that whole thing will get closer to 0. And so it'll
Right.
eventually be like 1 minus 0.
Right. So it converges to 1. So it turns out we can walk a mile. Whew. Thank goodness. You ever feel like, you're just going through life and progress is so slow, you feel like you're walking forever, you're just on the grind on this journey. Does it ever go anywhere? Math gives us hope. Even in seemingly infinite journeys can actually culminate to something. This one actually culminates to 1. It actually makes sense, which is pretty cool. We just figured out how to add an infinite number of things, not in the context of some integral or Riemann sum, but as a general idea. We figured out what it means to add. What is the essence of addition? We applied that essence to an infinite. Yeah, Vanessa Carlton walks 1,000 miles. Okay, stop it. Okay. All right. So yeah, a half plus a quarter plus an eighth plus ... going on forever, that adds up to 1. And we can define this to be the answer. You can actually show that, and some people might, have a problem with this, like, yeah, but we'll never actually get to 1 though, because we'll never actually add up every. No, it's 1. Like it is 1. Like 1 is equal to that infinite sum. Like you think of them as 1 is the same, they have to be the same. Because what you can show is that the guy on the left, a half plus a quarter plus an eighth, it will never add up to anything less than 1, and it will never add up to anything greater than 1. So if it's never going to be less than 1 and it's never going to be greater than 1, what else is there to be? It has to be actually 1. It is literally 1, adding up all these guys, right? Which now, last week when I asked about what does the sequence converge to, and I gave you the sequence 1, comma, a half, comma, a quarter, comma, blah, blah, blah. Someone said 2, and I think they were thinking of the series instead of the sequence. So 1 plus a half plus a quarter plus an eighth plus ... that actually adds up to 2. So there's actually a meaning here in adding things up, and it actually kind of makes sense even in the real world. If you were to take some length in the real world, find a systematic way of how to dissect it into an infinite number of pieces, then adding up that infinite number of pieces should give you back the original length that you started to cut up in the first place. It makes very intuitive and mathematical sense that something like this should be possible, and it turns out it is in this case. Now, a bigger question is, when can something like this work out? When does this actually happen? When does an infinite sum have a nice, meaningful answer? When does it not? Is it always the case? Is there always a meaningful answer? That's what we're going to do. Figure out. Let me put some space here. So yeah, we can walk a mile. The dichotomy paradox is solved. There is no paradox. We just had to make our notion of what it means to add something bigger. Or more comprehensive. So yeah, now of course, this, as you can probably tell, is going to be tedious. Like if we have to build this list and then figure out how to describe a general term in this list, and then, it can get tedious, to be fair, but this is the foundation, right? So this is kind of like when you first learned about the derivative, and the only way you knew how to compute one was the limit as h approaches 0, f of x plus h minus f of x all over h, right? And that was pretty annoying until you figured out a shortcut for it. But there's always benefit to knowing where things come from, because every now and then your shortcuts don't work, and you really have to go back to first principles to figure something out. So it's very important that you guys understand what a series is actually doing behind the scenes. So later on, I'm going to show you shortcuts of how to get to this answer, but I do want you to, in the back of your mind, understand what's really happening, right? This is the construction that's really happening. And essentially, all our shortcuts take this into account behind the scenes. Before we move on, there are some important definitions that we need to get through, okay? So now we understand what it means for a series to add up to something. Whenever it does, we say the series converges to that thing. And if it doesn't, we say the series diverges. Now, given a series, here's a manipulation that we can do. We can look at the series and then we can take the absolute value of each term in the series and we can add those guys up. So the original series here is like A1 plus A2 plus A3 plus A4 plus ... and someone just comes and says, you know what, we're not going to add up A1, A2, A3, A4. Let's put absolute values around the A1, absolute values around the A2, absolute values around the A3, absolute values around the A4, absolute values around everything, right? Put absolute values around each term and add those guys up. If that guy converges, then we say the series converges absolutely. That is a very important definition, right? So that's what it means for a series to converge absolutely. It means that if I put absolute values around all the terms and play the same game that we played earlier, it's still going to add up to a meaningful answer, right? If the series converges, but it does not converge absolutely, we say that the series converges conditionally. What we're going to see is that there are certain series that I can add them as they are, and it will add up to a meaningful answer. However, if I put absolute values around anything, then it no longer adds up to a meaningful answer. Sometimes these series will have minuses in there, so it'll have some terms being added, some terms being minus. And what happens is the subtraction parts kind of whittle it down so you don't get infinity. But once you throw in absolute values and you get rid of all the subtraction and everyone's just adding absolute values together, then it gets too big, right? So there are times when we don't have absolute values and we can add things up and the pluses and minuses cancel each other out in a nice way so that we get an answer. But then when we take away the minuses, it doesn't add up to something nice, right? So there there's a distinction that we want to make between these two situations. So the situation where a series, if I put absolute values around its all terms and it still adds up, and remember, I'm putting absolute value around each term individually, right? So if I put absolute values around each term individually and it still adds up to something meaningful based on our previous definition, we say it converges absolutely. Otherwise, we say it converges conditionally. It's possible for it to converge without absolute values, but it doesn't converge with them, right? Now, yes.
Would they have to converge to the same thing?
No, not necessarily.
Okay.
And in fact, the conditional definition kind of hints to you that that would be the case, because it's possible for without the absolute values, it adds up to a number, but when you put in absolute values, it doesn't even add up to a number at all. So they are not the same. They're very different things. Incidentally, in our previous example, they happen to be the same because all these numbers here are positive anyway. So if I threw absolute values around this guy, it wouldn't make a difference, right? It would still add up to 1. So in this situation, it doesn't make a difference, but it possibly could. So they're not the same in general. However, when we add things up with absolute values around them, that is something that we want to know when it happens, because that means the series converges absolutely. Now you might say, why would we care? Why do we want to make things even more complicated? We're already adding up an infinite number of things. Now you're going to throw in absolute values. It actually is important, right? So, and of course, by the way, if something doesn't converge absolutely or conditionally, then it just diverges flat out, right? Now, why is this distinction in convergence important? Well, there's something called the rearrangement theorem that makes this important. So Riemann, our good old friend Riemann, the guy who invented the Riemann sum, who is responsible for how we do integrals today. Integrals existed before him, but he developed a new method of calculating them. So we do know that even Archimedes, again, in the hundreds of BCs, 200 to 400 BC, somewhere around there, could do integration. But Riemann came up with a new thing in his PhD thesis, no less, and this was in early 1900s. So about 100 years ago, give or take, is when integration as we know it came to be, right? So Riemann actually developed Riemann integration in his PhD thesis. And in that thesis, which was 100 plus pages long, on one of those pages, very innocently, almost inconspicuously, there was a theorem that he proved on his way to proving something else, and it was called the rearrangement theorem. Now, this theorem is a very peculiar theorem, and it says, yes, even though we built up infinite sums to work intuitively and mathematically, they actually behave very strangely compared to finite addition. So here's what the rearrangement theorem says, and this is why the two types of convergence are actually very important to distinguish. Let A and be a series, and suppose it's conditionally convergent, and let R be any real number. Pick your favorite real number, pi, e, a half, 0.732, doesn't matter. R is any real number. Then it is possible to rearrange the terms of the series so that it converges to that number R. It is also possible to rearrange a conditionally convergent series so that it diverges. However, if the series is absolutely convergent, then all rearrangements will converge to the same thing. Summary, what is he saying? Remember this whole idea we have about commutativity of addition? It doesn't matter what order you add things in. So if I add 2 plus 3, it's the same as adding 3 plus 2. It turns out that when you move on to infinite sums, this is no longer true. The order in which you add things can matter when you're adding an infinite number of things, at least in one case. If the infinite sum you're looking at is conditionally convergent, then the order in which you add the terms will matter. In other words, commutativity of addition breaks down in the conditionally convergent case. If a series converges absolutely, however, then no matter how you rearrange the terms, it will always add up to the same number. It will always converge to the same number. In other words, commutativity of addition, the fact that we can add in any order and get the same number, when it applies to infinite sums, it only works in the absolutely convergent case. And this is why knowing about the absolutely convergent case is very important. We need to know, when does it actually make sense to rearrange the terms in a sum? And you might wonder, well, I mean, it's an infinite list and I'm adding it up already. Why do I need to care about order? Well, for a lot of reasons, not the least of which we're in calculus, right? So we're not only going to want to be able to talk about infinite sums, we're going to want to be able to do things like take derivatives, take limits, take integrals, and things of that sort. And it turns out that the integrals also have their own rules of how they play with addition, right? So if we wanted to be able to take an integral, for example, of a1 plus a2, and we can describe these guys as functions of x if you want. There's going to come a point where we're going to want to be able to take an integral of something that looks like that. But we know our integration rule says that this means we can actually distribute the integral across the sum. Now, here's the problem. If I can rearrange the terms of the sum and get a different answer, it means that my integral will never agree with itself, right? If it's possible, if we can rearrange this, if this changes with rearrangement, then so does this. So now, if I kind of like not care about adding the order of my terms, now I end up in a situation of, you know what, if I'm integrating a series, now I have to worry about the order in which I'm integrating. And that shouldn't make sense. It shouldn't make a difference what order I want to integrate my functions in, because I want to be able to apply integration techniques. I want to be able to integrate this part first and then leave that part for a more complicated technique, and then do a substitution on this part and by parts on this part. I want the freedom to be able to deal with my integrals individually across the sum. If the sum itself is changing values on me, there's no way that I can do this and have any meaningful answer. It's like everyone would do an integration and we can all end up with a different answer, and someone can end up with no answer at all, and we'd all be correct. Doesn't make any sense, right? So knowing when it actually makes sense to not only have an infinite sum, but to be able to manipulate it mathematically, to be able to move around the order, to be able to integrate and differentiate. In order for all that to work out, we need something that's called absolute convergence, right? And so that's why absolute convergence is important. And there are going to be times where we're going to want to be able to distinguish between convergence. We're not only going to want to know that a series converges, but we're also going to want to know that a series converges absolutely, because that will have all sorts of consequences for us down the road, right? When it comes to calculus and doing our calculations and et cetera. That being said, let's look at some properties of series. And you'll notice that the list of properties here is very short because series are very finicky. They don't like all the rules don't apply to them like limits, right? So limits taking a limit is a very nice operation. A lot of our mathematical rules like community of addition, community of multiplication, distribute across sums, distribute across products, distribute across all sorts of things. Like limits are like that. Series are not like that, and most math operations aren't like that actually. Series is no exception to this. So there are two nice properties that we know about series for convergence series. Let me emphasize again. Let's talk about convergence series. I meant to do that. Okay. One is that you can actually let's move this out of the way. What is this? It's an empty box. Here's one thing that we can do with series that can work essentially all the time once the series is convergent. It doesn't matter if it's absolutely or conditionally. You can factor constants out of the series. And this is something that we sort of knew before. So one basically says that if I'm adding up a bunch of terms like this, what it means is I'm taking, CA1 plus CA2 plus ... But that means I can factor out a C. And so that's just C times the series, right? So we can factor constants out. That actually makes sense with our interpretation. We can actually distribute series across sums. So it turns out that if you have this guy, this is like saying you're taking your A1 plus A2 plus, and then you're plussing or minusing. Let me actually write down the other way. It's like you're taking A1 plus B1 plus A2 plus B2 plus . Essentially like taking the A's. So these guys actually work out. And again, it looks very straightforward, what I'm writing down, but it's actually not. You actually had to prove that these guys work because like I said, when you're taking infinite sums, weird things can happen. The rearrangement theorem is proof of that. So this had to be proved in detail, but you can essentially take this as a given. We can factor constants outside of series and series can distribute across sums. Here's a warning though, series do not distribute across products. So do not assume that this is true. That is not true, right? It's a very common mistake for students to think that's true. It is not true. In fact, if I take, say, the series of A n, B n, this is pretty much always strictly less than, could be less than or equal to this. And that should make sense because this guy is like A1, B1 plus A2, B2 plus A3, B3 plus going on forever. Whereas this guy is really like A1 plus A2 plus A3 plus ... times B1 plus B2 plus B3 plus ... And then you have to like expand the parentheses and you get A1, B1 plus A1, B2 plus A3B3 plus A1B3 going on. And then you would have plus A2B1 plus A2B2 plus A2B3 plus ... And then we'd have A3B1 plus A3B2 plus A3B3 plus ... And you'd realize that these guys over here are only just a few of these guys over here, right? You're actually adding up all those guys, plus you're adding up a bunch of other terms. The only way these guys are equal is if those other terms happen to be zero, right? Or they happen to add up to zero. So in general, though, as you can see, the guy on the right is going to be bigger than the guy on the left. So series do not distribute across products, so that's very important. They distribute across sums, and we can factor constants out. There's also a nice little kind of series that your textbook talks about. We are not going to talk about those, the telescoping series. It's pretty cool. You should look into it if you have the time, but especially with a test coming up this week, I wouldn't look into it this week. Yeah, so that is the introduction to series. So like I said, dealing with series is very, very, very super important. We do actually want to know how to deal with these objects. So important things that you need to know. A series is the sum of the terms of a sequence. There is the idea of the sequence of partial sums, which means you're adding up the first n terms of a sequence, and then you kind of imagine that you're taking a sequence to measure these partial sums sequentially. It's too many S words there. Okay, we say that a series converges to a number if its sequence of partial sums converge. So essentially, if you can come up with a formula that describes the partial sums, you take the limit as n approaches infinity of that guy, and you get an answer. That's what the series converges to. We actually did an example where we actually built up that list, took the limit, and it added up to 1, which makes sense intuitively as well. So that was nice. There are different kinds of ways that a series can converge. So there's only one way for a sequence to converge, but when it comes to a series, the sum, there are 2 kinds of convergences that you can have. You can converge conditionally, which means you converge as is, provided that we don't touch anything, we don't rearrange the order or anything, and you would add up to some number that we can count on. However, if we want to rearrange and have meaningful answers, or sometimes you just want a different class of convergence, the gold standard is converging absolutely. This means even if I put absolute values around all the terms, get rid of any negatives that would have been there, we still add up to a number. That means like this guy really converges. Like there's no way to stop it converging. It converges under some extreme cases, some extreme standards. And it turns out that once a sum converges that strongly, it permits a lot of the other nice rules that we love from mathematics, like commutativity of addition and a bunch of other things that would work nice in the absolute convergent case, but not the conditionally convergent case. So that was the rearrangement theorem. We have that thanks to Riemann once again. And yeah, the rearrangement theorem let us know that as long as if we're doing an integration of a series, if the series is absolutely convergent, we don't really have to worry about it too much. We can kind of follow our integration rules for the most part and not really even worry about the series. We can actually integrate term by term. And of course, that creates a new kind of series, a series of integrals that of course we want to know to be able to answer that, but that we'll leave that for another time. So yeah, calculus and all our other old math rules can work out for absolutely convergent series. For conditionally convergent series, the math breaks down. They are still useful, but they're not useful for everything. Like we can't do calculus with a conditionally convergent series. Properties of series. 2 basic ones, don't have a lot to work with here. We can factor constants out and we can distribute them across sums. We cannot distribute series across products. Very cool thing called a telescoping series. Basically, this is a series where terms cancel each other out so that it looks like an infinite series, but it's almost like there's a finite number of guys left over after all the cancellations happen. So I won't talk about that. The basic idea here is partial fractions. You'd use partial fractions, right? This is 2 fractions. You realize that it's 1 fraction subtracting another fraction, and then you'd realize that the subtracting fraction cancels out the adding fraction infinitely often so that we only have a finite number of terms left over and we can actually add it relatively easy. So that's called a telescoping series whenever that happens, which they're pretty cool, but we're not doing them. So that's series. At least that's the idea. That's the introduction to series. That's what a series is. Now, of course, as I was mentioning, it's going to be kind of annoying for us to actually add up series based on that main definition. Right? So yes, we understand the method, but I mean, it can be annoying. I mean, depending on how the series looks, coming up with that SN formula can be a real nightmare. So we kind of want some other shortcuts. So this brings us to the chapters. Well, it's the last part of 11.2 going on through 11.6. Where we're going to learn some tests by which we can test whether or not a series converges. Now, most of these tests, the vast majority of them, we're going to look at around 10. So again, it's going to be kind of like integration techniques all over again. You're going to know a bunch of techniques for how to test series, and you're going to have to know when to use which one. We'll talk about that later on. But we'll go through a bunch of tests. And pretty much only 2 of them, and I'm including the telescoping series in that, only 2 of them actually would tell you what the series adds up to. Figuring out what a series adds up to is a very difficult problem in general. However, knowing that a series converges to something is a much easier question to answer. And so that's kind of the focus of the sections 11.2 through 11.6. We're trying to figure out that a series converges. We can worry about what it converges to later on. And even if we can't figure out what it converges to, a lot of times we'll be able to approximate what it converges to, and that'll be good enough for all practical purposes. So we can have an infinite sum, and we want to know, does it add up to something meaningful? Figuring out what that thing is very, very difficult in general. However, figuring out that it adds up to something is easier, and we have these guys to help us out on that in that endeavor. Okay, so this brings us to the series convergence test. There is a handout for this on the class webpage. The direct link is here. But yeah, we're going to go through these guys. I'm going to show you how to use all these tests and when to use them. And then again, at the end, I'm going to recap and talk about all these tests in general, when you would apply which, and what you can conclude based on it. But the idea here is basically, how do I know that an infinite sum is going to add up to something meaningful without me playing that game that we were playing in the last section, right? I want to save myself some work, and tell me a shortcut for knowing that this thing is going to add up to something meaningful, okay? That's where the series test comes in. And for today, I actually only want to talk about one of them. It's the easiest one to talk about. It's the kth term test. It's the guy that's in the second row here, right? So this is the first main test. And this guy, this is kind of like, he's in the hierarchy of like your basic rules for integration or integration by substitution. It's normally one of the first techniques you're going to try because he's the easiest one in general to apply, and you can get an answer. What he has to tell you, he can tell you very quickly. So in terms of hierarchy of all these tests, the test for divergence is high up on your list. It's going to be one of the first things that you want to do. We'll talk about that though. It's not the very first, but it's very, very high up there. It probably is the very first. It's kind of tied for the very first. So this is called the test for divergence, aka the divergence test, the nth term test, the kth term test, aka the limit divergence test. They're all sort of the same thing, but they'll either have like divergence in the title or something like the nth term or kth term in the title. And here's what the test says. So all of these tests, they have their own proofs of why they work. We're not going to focus on that at all in this class. I'm just going to tell you what they say, what conclusions we can draw from them, and that's kind of contained in this table. So here's the test. Here's when we can use it. Here are what conclusions we can make from the test. So the first one is called the test for divergence, and here's what that test says. Suppose you have an infinite series, right? Series of an. If the limit is not 0, if the limit of the an term, right? So not the Sn, the an, just the guy that you're looking at in the series, if that limit is not 0, then the series diverges. That's it. That's basically all it is, right? You're basically using a limit to determine what happens to a series. I do want to point out, note, as its name suggests, this tells you about divergence. It's called the test for divergence for a reason. It cannot tell you about convergence. Otherwise, it would be a really bad name. Okay, so that's the first important thing. But other than that, the test is pretty simple. You have a series, an infinite series. Take the limit of the term that you see, the an term. If the limit is not 0, it diverges. Basically it. So very easy to apply, something that you don't really have to learn any new techniques. We all are very good with limits at this point. So let's actually jump into this. So let's say, yes, Brooke, that's definitely what I mean. And that's something we're going to explore a little bit more later. So let's look at this first one. Hopefully you can see that very well. This series, n to the n over n factorial. Well, we can look at this. We can say note. If I take the limit, and it's always n goes to infinity, I don't really have to write it, of an, which is the limit of n to the n over n factorial. What is that?
Because the numerator is going to grow faster than the denominator, isn't it going to approach infinity?
It's going to be infinity, right? So that limit is infinity. So see, like I said, it should be very quick for you to get to the answer in this. That's infinity because we're great with limits now. In particular, infinity is not 0. Therefore, we can say the series diverges. And then I can say by the divergence test. So a lot of times when we make a conclusion, we do have to justify the conclusion. So I can say by the divergence test, the series diverges. I took the limit, it didn't approach 0. Test for divergence says diverges. Here's another one. So if I look at this, note, limit of 5 minus 7n plus 3n cubed over n cubed plus 2n plus 1. What is that equal to?
3.
It's equal to 3.
Which
Look at that, very
not
quick.
0.
It's not 0. It happens to not be 0. That's the most important feature about 3 in this case, which means this series diverges. Look at how easy that is. I can tell you that it's not a meaningful. Like I can't, right? So I can tell you that this is not going to add up to anything meaningful. This series diverges. By test for divergence or whatever. So I'm not even going to waste my time looking for that formula. I don't need to. I know that it's not going to pan out. Absolute value of sine x. Note. What is that?
It fluctuates between 0 and 1, but there's no like, it does not exist.
Does not exist would be the best answer here, right? In particular, that's not 0, right? So the series diverges.
Can I guess the next one's also going to diverge?
Well, we are talking about the test for divergence, right? So okay, let's look at this one. All right, note. If we take the limit of 1 over n as n approaches infinity, what do we get?
That's 0.
We get 0. Okay, what does that mean?
Would it
It's
converge?
inconclusive.
Oh, just kidding.
It is not divergent.
No, but someone said the answer. And now he's like, just kidding. Right. It's a very common mistake, which is why I put this in red. Remember, it cannot tell you about convergence. So if you saw the 0 and you're thinking, oh, that means it converges. No, you're already wrong for that line of thinking. It cannot tell you about convergence. In fact, no conclusion from this test. You need something more sophisticated to talk about this guy. In fact, this guy does diverge for other reasons. But I do want to point out a useful example as well of this example. Like if I had 1 over n squared, right? So here, the limit of 1 over n squared is also 0, but this actually does converge. So on one side, you'll see that the limit is 0, and it actually diverges. Actually, this is a very famous series that diverges. It's called the Harmonic Series. I have that in the notes later on. This series over here, though, 1 over n squared, n goes from 1 to infinity, summing that. Then this one actually converges. Okay, can anyone guess what that converges to? So this guy is like 1 plus 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, etc. Can you guess what that actually adds up to? It's very obvious, actually. Pi squared over 6. I'm being sarcastic. That actually adds up to pi squared over 6. Yeah. So that's the test for divergence. Take the limit. If it doesn't approach 0, you know for sure it diverges. If it does approach 0, you can make no conclusion because it can actually go either way. You can have the limit approaching 0 and it diverges. You can also have the limit approaching 0 and it converges. The idea is some things don't approach 0 fast enough. So by the time they get very close to 0, we've already added too much. So it goes off to infinity. Some things approach 0 a lot faster. So very quickly, it's like we're adding nothing, while other things don't behave that way. So sometimes it's the rate at which they approach 0 is important. So yeah, in fact, this series is a very important series. It's called the Harmonic Series. Why it's called a Harmonic Series, it's actually attached to music. There's something called the harmonic scale. And this is actually used in music and in signal processing and harmonic analysis and all that good stuff. So that's a very famous series that diverges. It's a well-known divergence series. In fact, it's going to be a series that we're going to compare things to all the time. So we can say, this I know diverges because it behaves like a harmonic series, right? So it's a very, very famous divergence series. Also, the series 1 over n squared is a very famous convergence series because most of the time we draw parallels or contrast between these two. Here's one where the limit approaches 0, but it diverges. And here's another one where the limit approaches 0 and it converges, right? So these guys usually are talked about in the same breath. But the harmonic series is very important. This one the latter one converges to pi squared over 6, hashtag obviously. Yeah. So there you have it. We know about series, which is just the sum of the terms of a sequence. We know what it means for a series to converge. This means add up to something meaningful. This means that the limit of the sequence of partial sums converges. Series can converge in 2 ways. They can converge absolutely or conditionally, or they of course can diverge. And In general, it's hard to know exactly to what they converge. We were, with the dichotomy example, the mile example, we were very lucky. We're not lucky that often. So we need series tests to be able to talk about more quickly, more efficiently, when a series would converge, when it would not. And the divergence test is the first guy in the list, the first line of defense. That's the guy that's going to tell you when the series isn't going to add up to something meaningful right off the bat. Don't waste your time trying to figure out what this guy is. He's not going to add up to something meaningful. He's going to diverge to infinity, or it's going to fluctuate, and it's just not going to make any sense whatsoever. So that's the test for divergence, right? And again, it only tells you about divergence. So you take the limit of the thing you're looking at. If it's not zero, it diverges, right? And this is in contrast with sequences. In sequences, this guy as a sequence without the summation sign converges, but with the summation sign, it doesn't converge. So don't mix those two up. Students mix up sequences and series all the time. Don't. So if the limit doesn't approach zero, it diverges in any situation, whether it goes to infinity, whether it goes to some other non-zero number, whether it does not exist. As long as the answer isn't zero, diverges. If the answer is zero, you cannot make a conclusion based on that alone. You need something else, okay? Because it can go either way. And these are two very famous examples that illustrate that. The harmonic series on the left and the squared of the harmonic series on the right. Yeah, and we'll stop there for today. So hopefully that was fun. So today, the test on Friday is everything up to the divergence test. And of course, in the bonus, I'll ask you about these other tests if you have time to study for anything further. But basically now you know the idea. These tests are basically going to tell you if something converges by following what they say. So here you'll see the kth term test, which is what we did. This can work on all series, and basically you just take the limit. If the limit is not zero, the series diverges. So it tells you how to make the conclusion, right? So this is the divergence test right here. And if you studied everything we've done and you're pretty comfortable with it and you want to go ahead, what you can do is you can read the rest of things in this table, try to apply them, and maybe you can get some of the bonus points. But we'll end there for tonight. Thank you for your attention. I will post all the notes again here so you can look at some examples that I would have done with you guys, or that I'm going to do with you next week. You can try your hand at them, read the little blurbs and the definitions that I give you, and you can try them if you want, but it's not completely necessary. If you know everything up to today, you should be in good shape for the test. You only need to go further if you want a chance at the bonus problems. Okay, I think any final questions before we leave?
I have one last question. Will the stuff that we see on the test be in similar like difficulty to the things that have been on the quizzes and the homework?
Yeah, pretty much, except for the non-definitional things, yeah. They're going to be roughly the same difficulty level. So once you go through the practice test that I posted online, and you go through all the quizzes, and you go through the problems that I suggested in the syllabus, you should be fine. You shouldn't need a calculator. So if there's anything that asks you to round something to 6 decimal places, you don't have to worry about that part for the test. Just write down your answer in exact form. But yeah, pretty much the same level of difficulty. It's just going to be an hour, and you have to show your work. Okay. All right. We will stop there. I believe I have office hours with one of you, and I will see you later. As for the rest of you, I will see you in the next one.